Welcome, everyone. My name is Sam Agan with Accutech, and I'll be moderating today's webinar. First, some information on the meeting platform. The navigation bar on the left includes a button to make the presentation full screen, a button to switch audio to phone, and a Q&A button to submit any questions you may have, which will be answered at the end of the presentation. Today's webinar on inherently safer design is the fourth of Accutech's 5-part webinar series on process safety topics. Slide, please. Founded in 1994, Accutech is a global leader in process safety and security, providing management and technical consulting services, world-class training, as well as enterprise risk management software. Today's session will be led by one of Accutech's ISD experts, David Moore. David is the president and CEO of Accutech, with over 4 decades of experience in process safety, security, and fire protection. David was also the lead author for the Center for Chemical Process Safety's guidelines for inherently safer chemical processes. I'll hand it over to David now.
Thanks very much, Sam, and I thank all of the attendees for taking the time out during such a busy and unusual time to learn about inherent safety and to discuss this topic, which is very near and dear to me. As safety professionals, you know that we're all driving toward the same goal, which is to continually improve process safety performance. And this is not a simple task for several reasons. One is chemical process safety is a complex subject, and the chemical processes that we work with are complex issues. And so achieving excellence, which of course it means zero incidents, is very, very challenging. So we unfortunately have not achieved that entirely yet, of course, and we're looking for breakthroughs. And I think that inherent safety is a 50-year-old breakthrough that is just waiting to happen. And so I hope that this discussion inspires you to look into inherently safer design more thoroughly and to see the potential that it has to help all of us. So ISD is something that you probably have experienced or know something about. It's a topic that's been around since the 60s, originally developed and coined by ICI in the UK in the late 60s. And Trevor Kletz, one of the most prolific writers there was in the process safety field, was highly known for this topic. And he had a famous saying, "What you don't have can't leak." And that philosophy was something that he discovered from years of watching all there is to do about process safety. And he basically concluded that one of the most important items is inherent safety. And it's very pragmatic. In essence, let's take it from the top. I mean, examples of inherent safety would include finding a way to substitute a chemical that's more benign for one that is highly toxic or flammable when you're in the development stage of a new process in order to affect a dramatic change in the hazards of the expected operation. Or maybe the transportation of chemicals. You find a way to limit chemicals you transport, or to limit quantities, or to avoid transportation altogether through hazardous populated areas. Or maybe it's involving the process facilities themselves in the manufacturing. There are techniques that you might use to reduce the reactivity, reduce the hazards being present, or even in commissioning. So in a nutshell, there's plenty of examples throughout history of the industry of us making smart decisions that you could call inherent safety. What I'm talking about is to organize that into a concentrated effort and get the maximum value out of it. Now, a lot of what we're going to talk about, as Sam just mentioned, comes from the fact that we just completed the 3rd edition for CCPS, and this is now published and available from CCPS. And it's an improvement over the 2nd edition, which we also wrote. And this is the source of much of the content in this webinar, which you're welcome to look at this or to contact me if you had questions going forward. The typical approach to process safety is to do the usual things that you all do every day. Identify hazards. The awareness of those hazards means that you then determine the necessity of various layers of protection, and you're focusing on reducing both the likelihood of those hazards being realized as well as the reduction of the consequences should they occur. And this is good practice. But the ISD approach says, let's not forget that maybe you can affect the hazard itself. And that's what you should focus on. So yes, you have to identify those same hazards, but then once doing that, rather than immediately thinking about how can I apply layers of protection to reduce those hazards by simply reducing the likelihood or the consequences, let's try to eliminate or reduce the hazards themselves. And that sounds trivial. It isn't always. And I think sometimes people think it's impossible because, after all, I'm in the business to make this chemical. And so they discount this as being very effective, and they focus on layers of protection and the hierarchy of controls other than inherent safety. Well, if you notice in yellow under step 2, we've inserted this apply inherent safety principles as the first strategy following the identification of those hazards. And the reason is you may not need all the rest of this. You may not need layers of protection, administrative controls, including training, expensive inspection programs, expensive safety instrumented systems, fire protection systems, and the like. And that sounds almost too good to be true, but I can tell you that we have become attuned to this, and we always ask these inherent safety questions first. And often we find ways that whole sections of equipment may be modified, chemicals may be eliminated, other choices may be made, and it's very, very helpful to reducing that risk. So it's a fundamentally different way of thinking about the design and the operation of chemical plants and processes as you're both engineering them and operating them. And if you think always about how can I eliminate hazards rather than try to add on or bolt on safeguards and equipment, you're on the right track. And honestly, you have to get into that mindset. I notice that all too often when we're presented a process for a HAZOP, the first thing we think about is what is the hazard? And the second thing we think about is how can I add some ragged gap safety control, such as a detection system or a pressure safety valve or what have you, to be, quote, in compliance and to manage these events should they occur. This is a different line of thinking. And I think if you can achieve this, you're going to end up with a simpler, more robust process that has the absolute hazards, if you will, wrung out of it to the extent possible, and you're left with a residual risk that could be far less and far more manageable. Now, the way you go about this is through the application of 4 simple strategies. If you read some of Trevor Kletz's publications, he mentions about 8 or 10 of them. And what happened in version 2 of the CCPS guidelines is we recommended consolidating this down to a simpler set of strategies. And the reason for that was to try to keep it simple so that people would understand it and it wouldn't be too confusing. So minimization is the idea that best case scenario, if I could get rid of a chemical that I don't need, maybe an ancillary chemical like a solvent that's flammable, and I can perhaps substitute. If I can't get rid of it, I have to substitute it. And I put in place either no chemical or one that's a whole lot less flammable, let's say. I've made a contribution, perhaps. And of course, the question becomes, well, what have you sacrificed? And that's to be seen. But I put my safety hat on first and challenge the design and don't take for granted the original proposal necessarily until I ask. Because often it's like anything in life, if you don't ask, you don't get. And there's also moderation, which is admitting that, well, we can't really eliminate the chemicals. Maybe we can't change the size of the vessels or what have you, but perhaps in the way in which we operate it. We're not operating in the same range. We're not operating in such a sequence or at such a temperature or pressure. And these are opportunities to keep us out of a more hazardous range. And the last one is simplification. This has many, many purposes. One idea would be the idea that the more complex a process may be, the more opportunities there are for errors, human errors, leaks, etc. So there's various ways to look at simplicity, but it's all good when it comes to safety, that if I can reduce the complexity, it's easier to train. It's less likely to make a mistake. There's less congestion. There's less congestion that may amplify an explosion. There's less leak points and so forth. So I think this is the principle, and you probably know what I just said here, but let's talk about a few other details, like there are viewpoints. We brought this point into the latest guidelines. The idea that I saw was that everybody talks about inherent safety as though it's go, no go with a certain process chemical. Like we don't like, let's say, chlorine, or we don't like ethylene oxide, or we don't like one thing or the other. And we think you ought to either substitute or no longer be in business. And this is very threatening. And so people get hung up on the idea that there's only this, what I call macro view, which is you have to use an alternate technology. You must substitute the entire process. What I found is often that's not feasible, and it creates somewhat of a fighting line where people put a line in the sand and say, you know, I'm not going to do it. We're in business for this, and there's no progress. Whereas with micro view, you can make progress at one cut at a time. So can we take a particular vessel in this process and make it redundant? It's not really required. Can we use a different catalyst? Can we simplify DCS controls? So think about this. The majority of the contributions that we make when it comes to inherent safety are micro. But the sum of dozens of micro equals a very good change. I often say any move in an inherently safer direction is a good move. Now, the other idea is the order of inherent safety design recommendation. And I mention this because I like to encourage people to make the highest order. So this is like in the range of impacts that you may have with your recommendations. Of course, let's aim high. Let's try to eliminate the chemical. Let's try to make the biggest change we can. So while I'm accepting of the minor as opposed to the major changes, I'm not aiming low. I'm aiming high. Now, what I have noticed is everything I just said is fine. A lot of people have tried it. They've tested the water, they've put their toes in, and haven't really consistently done it. And one of the reasons I think that is that they're not encouraging it enough, perhaps. For example, how many companies actually have a written policy that says, we do IST studies, they must be done before we have a project go into feed engineering, and at various stages, if we make any changes. How many companies have a written procedure on how to actually conduct an IST study? How many companies actually do IST studies as either special studies or they consider it as part of their PHAs? And as a matter of fact, have we given our people training so they know how to conduct this? So I thought it might be interesting if you could use your poll buttons, and if you in your company have either A, B, C, and or D, please select all that are applicable. So in A, you would have a policy. B, you would have a procedure. C, you would document this kind of consideration in studies very consistently. It's part of your corporate culture to do this. And D, you've given training. I'm curious what the answers are. We'll give you a second here.
All right, just a couple more seconds. I think everyone's votes are in. So we have 40% of the respondents have a policy, another 40% have a procedure, 80% do conduct studies and document them, and the 20% have training on ISD.
Right. Well, that's interesting. Now, I mean, obviously, we could improve that, right? And I think that's maybe a picture of the way industry is, that a lot of people have tried it, so they could honestly say we've done it, but they really don't have necessarily a formal procedure. They just expect that this is considered. Maybe they say, and you shall consider inherent safety, or perhaps they have a checklist, and they say, oh, and when you're done with your PHA, use this checklist. And we'll talk about that in a moment, but what we think is if you adopt A, B, C, and D more formally and really encourage it and have a discipline about it, you'd be surprised at how the change that may come about. Now, I'm a believer of this premise that ISD can and should be widely and routinely used, not just at one time, like a one-time study. We get in this rut, really, where almost out of necessity, we can't do PHAs every day. We have to kind of do them periodically. That's fine also with ISD studies, but really we shouldn't get in the mindset that one ISD study way back when we were first thinking about this new process is all we need to do and then forget it. Because things change, and we know that lesson we've learned for PHAs. Well, why not apply the same for inherent safety? So I would have to argue there's a lot of factors that we've seen that are limiting the use of ISD. Some confusion on exactly what it means, and maybe a lack of appreciation of how much you can get out of it. And not everybody has a strict policy or procedure, nor do they have good written procedures about how to execute a study. Now, another thing I'd like to bring up is that if you take inherent safety as a safety philosophy, that's even better. In other words, every employee every day is presented with some decision that they have to make that involves safety in our business, not just the PHA teams and not just an occasional ISD study. So I actually believe that providing this kind of high-level training to everybody when they step into a situation, whether it be an MOC, a PHA, a PSSR, an engineering project, a research project, they're going to be thinking that my company wants me to emphasize inherent safety first. And they will be advantaged. I think they'll be turning out lots of good work without being forced to do a study. That you would be impressed, because companies that we've worked with that get what I'm saying are quite excited about it, and you see them making these conscious decisions and documenting things other than just in a special PHA study. Now, this figure was published in the 3rd edition, and this is to say that the 4 strategies have wide application to all of the, in this case, 8 defined steps of a process lifecycle. So starting at the top with a concept, you can imagine I have a concept in mind. Let's have a conceptual meeting, perhaps a formal analysis of hazards. You should be thinking of inherent safety, because there's nothing quite like nipping something in the bud if they were thinking of placing a very hazardous process right next to some public area that would not be a good idea, and you'd have to have excessive controls to try to manage this risk, perhaps we can stop it there. But everyone believes, okay, that's the place for ISD. I don't see that it being a good place to do this when you're in the operations and even maintenance phase. Most of our industry is constructed and operating, and that's actually where we've made a big impact. And I would absolutely tell you that inherent safety studies of existing facilities are also extremely useful. Now, there's a couple different ways that you can do a practical study. I say practical because if you follow the industry, there's lots of papers about indices, and those are useful, particularly people that use something well recognized like the Dow Fire and Explosion Index. They'll do a study, they'll analyze that index value, then they'll look at alternatives and they'll say which one is inherently safer by relative risk. I'm really more interested in specific risk studies because to me, there's nothing that's cookie cutter about this. You have to look at a process, get creative, think about what the opportunities are, and actually make a difference by some smart engineering. So there's two ways, and that is independent studies, which really means a study that I'm doing only to concentrate on the ISD opportunities. Not that I don't care about the other things, but that's usually the purview of the PHA, et cetera. The second way is to integrate your PHA studies by incorporating ISD concepts. I could probably survey actual studies and find almost no mention whatsoever of ISD concepts. Almost everyone identifies a hazard and makes certain that we have the proper shutdown, isolation, fire protection, etc. So forcing it into the PHAs makes a smarter PHA study. That is the advantage, and that's why the last statement there is the most practical and effective way in the long run. Unless you have a need for a special ISD study, the most practical way is incorporate it. In other words, improve the way you do your PHA studies. So the steps are kind of like a PHA to begin with. And this involves, having a team and the right people and conducting an assessment of the nodes once you understand the process. They don't have to be the same. Like if you had 50 nodes for a complex process for a PHA, maybe you only need to consolidate and now you have 10 that you're studying for the ISD. Because what you're doing at each node is you're iterating through asking about those 4 strategies. And you might say, well, we can do that one time with a checklist. No, I'd say that's too high level, too general. You get a lot more out of this when you narrow it down to at least some consolidated number of nodes. And by the way, the typical PHA hardly talks about this at all, like I said, and focuses on these other layers of protection. So one of the things we recommend is try this, try interjecting this into a PHA, and you'll be surprised perhaps at the number of things that you not glossed over, but you weren't thinking quite in that mindset. So then what you do is you understand the hazards. Now, you could use common knowledge of hazards, or you could use previous studies like a HAZOP or a HAZID. And the idea is you're taking one of those hazards and you're challenging it directly by saying, how can I tear that apart, eliminate it, reduce it? We don't often do that. We often talk about how can we put a barrier between us, and lots of barriers. And barriers are good, but barriers can be weak. So what's better is to eliminate that if you can. And it isn't fantasy to eliminate or minimize hazards. It can happen. So then you analyze what we call opportunities. We call them opportunities because there's usually more than one opportunity of how you might treat a hazard, and you're not sure at this point as to whether those are actually viable, what we call feasible. And you do all 4 of the ISD strategies, and you concentrate on the first order. Remember, our first order meant try to go for swing for the fence first. And if that doesn't work, then you could back down to a lesser improvement. I'd rather have a 10% reduction in hazard than ignore it altogether. And then you determine the feasibility. And feasibility is often complicated. I've been in studies, ISD studies, where the feasibility was obvious. Do we need that? No, it's actually abandoned. We should make a decision to isolate that and dismantle that and get that equipment out of here because it's unnecessary. Whereas other times, can we substitute a catalyst? That is something you don't want to just say, sure, it's feasible and possible and let's go for it, because there's potentially lots to think about. So these studies are more about identifying opportunities than they are about truly making final decisions on design changes. And then you make recommendations, and the recommendations might be to consider this or to consider that. And of course, they're screened out by the team, but the team supports the decision. And in the end, you're going to be left with some, we call it residual risk, and the adequacy of the layers of protection can also be looked at. So the first thing I did is attack the hazard. The next thing I do is try to make sure that the passive, active, and administrative controls are as inherently reliable as possible. And so I hope to, let's say I conceptually eliminated 80% of the hazard. That's a big difference, but that last 20% might still be significant. So now by looking at those layers of protection in an inherently safer way, I might come up with simpler and more reliable safeguards as well. Now, one quick way to do that often is the case, as I said before, is to use a checklist. A lot of people like checklists, and we use them too. They're rigorous because they are consistent and complete. And let's say that they come from a book, they got to be right, and they have a lot of information that maybe your team hasn't thought of because you haven't experienced it. So you take a good reference, like the CCPS guidelines has a checklist, and there's 100 plus 200 questions there. And, you use this every time on every process and filled in the opportunities, the feasibility, the recommendation, and so forth, you're doing an inherently safer design study. And maybe it's standardized because you're always using the same checklist. So those are the advantages. But I'd like to ask you this. Are there any disadvantages of just using a checklist and nothing else? So what are the disadvantages of only using a generic checklist? Is it A, that a generic checklist may miss specific process opportunities that aren't mentioned on that checklist? Is it B, that by the monotony of using the same checklist alone, you're not being as creative? Is it C, that checklists can simply be incomplete or dated and the version you have isn't maybe the best and we're all limited to what was on the checklist, so we miss a hazard for that reason? Or is the answer all the above? So here's another poll. Would you mind answering this as either A, B, C, or D only, please? And I'm curious what you think.
All right, just a couple more minutes. All right. And we'll show the answers to everyone. Looks like you had a few votes for A, B, and C, and 95% of the votes were for all of the above.
Well, I just can't trick you here. I mean, obviously to me, all these can be potential problems, right? And so all of you are correct, but I think the best answer is be cautious because of all of these, A, B, and C. And checklists are the number one thing that I see being used for inherent safety analyses, often all by themselves. if they just attach a checklist that they went through and they said, not applicable, not applicable, not applicable. Oh, here's one. It's not feasible. That's not really the most thorough inherent safety study I've seen. Now, let's just walk through the world of inherent safety studies here. For one thing, if I'm a chemist and I'm being charged with helping to put together concepts for a new process at our plant, and the end result is we want acrylonitrile to be produced, I might look at the conventional process, which uses hydrogen cyanide, and get on with it. And then we take a typical design package from a vendor that licenses this, and we start building it. And then what do we focus on? We focus on making sure it has sufficient safety instrumented systems, detectors, fire protection, etc. You might say to those people, when you're looking at this, we want you to formally study inherent safety. What are the options? And I'm not a proponent of this particular option necessarily, and certainly not in every case, but I'm just pointing out to you that there are options on how to make acrylonitrile. And very often, these things are ignored because of tradition or because of cost, and they should be looked at, particularly if you have a difficult populated proximity of population or what have you. It's the lesser of two evils, I guess you'd say. And here's another example. Maybe you want to make methyl acetate, and the conventional process involves about 10 different major process vessels. And that may be an incredibly efficient, well understood, stable, et cetera, et cetera. There may be another one, though, which is involving a lot less equipment. And this is a reactive distillation process, which, theoretically only involves 3 major vessels. Now, for me to say that that is better than the first one is a misnomer, because I have not studied it and I have not evaluated the specifics. If you are, what I'm condoning is the idea of encouraging engineering teams to look at alternatives of where they can eliminate vessels, eliminate points of release, simplify a process, etc. Don't just let them give you always as complex a process and then you have to deal with it in terms of managing the risk. So those are things that are done in the early stages, but I'll tell you what most studies are. Most studies is we have an existing plant or we have a design that is somewhere in FEED or in engineering phase, and by then they're pretty well committed. So now what can we do? And most people at this point would say, well, ISD is over with. There's nothing to do. Think of it like a PHA study, and let's attack it one step at a time. Get prepared, see if there are alternatives, see if there's anything that can be done at this stage, understand the process, then go through in a node way, like we just described, all the ISD strategies, and identify all of the possibilities, what we call opportunities. And then what we do next is interesting. While I was criticizing ISD checklists as the only method, we think it's useful after you've had that creative prior step of asking the team to identify hazards and directly identify what we can do about it using the strategies. Let's then go to the ISD checklist, because some of those checklists have brilliant experience-based ideas that you don't want to forget about. And then you prepare a report that formalizes all this and then follow up and make sure it's getting done. So it looks a lot like a PHA. Here's a checklist worksheet. You notice that it has questions. Let's assume those questions, 5, 6, 7, 8, for example, are defined, and the rest of it's blank. So the team looks at the first one, can we minimize the length of any hazardous material piping runs? And very often this is entertained at a gross level of the entire process. And I could tell you the majority of the answer of that kind of a question is no way. So what you would be better off is looking at it on a smaller scale. That's why nodes are valuable, because on the feed length, well, yeah, we're bringing feed from halfway across the plant and there's a closer tank that supplies it. Why are we doing that? And so there are things that you can do if you look at it more carefully. So you identify opportunities based on these questions. Then, of course, the feasibility. And by the way, sometimes you shoot it down yourself because you can see it's not feasible. And then what are the consequences that you're trying to reduce, and how powerful would this be in making that reduction of consequences? And likelihood is also considered. You can document that under the severity, likelihood, and risk. If you use a risk ranking, not a lot of people don't. You should, I think, just like we've learned in PHA studies, how valuable that is to give that risk perspective. And then finally, a recommendation. So this is not a bad thing, but I'm saying that if all you do is read off the 50, 100, 200 questions and fill them out, a lot of times those questions are not relevant, not applicable, or too general. Now, this is what we prefer to do. We prefer, as it says up here at the top, to split up into nodes, then to say, let's take each objective or strategy at a time. For example, minimization, and let's attack a hazard. In this case, they're in a reactor section, so they say, minimize the potential for runaway reaction in the feed to the reactor. Because through experience or through the HAZOP study, that was the number one thing they're trying to control for a process safety perspective. And the main cause is high water content from a feed tank that carries forward. So the first three columns pretty much summarize the hazard. That's either documented from the team's good efforts or it's copied over from a HAZOP study. And the last half of this is opportunities by which you can apply the concept of minimization in order to reduce that hazard. When we're done with minimization, we'll go to the other three strategies. And basically, you have a creative discussion. And again, we're trying these first order ones first, but we're happy to talk about second order ones. And we ask if there's anything that can be done here. And, ideas may come up about, well, look, can we switch to a different tank that has less water settlement problems? Can we make improvements to the water draw on that tank? There are various things, and a lot of this is standard engineering, but this focuses your attention on it rather than having a defensive posture all the time. And if you can eliminate the, let's say, water problem altogether, well, then so be it. You may have then eliminated quite a bit of additional safeguards, and certainly the potential for the failure of those safeguards. Now, ISD is pretty good. I, appreciate it a lot. There are pitfalls. We need to talk about that. And if you know who John Muir was, when he wrote his books on conservation, and he was a real environmentalist back in the turn of the century, last century, he basically said it when he was referring to the impact we may have on the environment by making some change to the environment. And he said, we try to pick out anything by itself and we find it's hitched to everything else in the universe. And what that means, simply put, is any change that we make could potentially affect everything else. So that's the biggest warning I can give you is I don't care if you're really sure that this is inherently safer, you got to be extremely careful that by throwing out this suggested change, whatever it may be, you may have caused a domino effect and complex interactions which cause additional hazards. And let's not forget that you don't build a plant only for safety. You build it for production, efficiency, reliability, security, economics. So you're competing with people. And you have to be careful not to force one solution that causes another one. Now, a big part of that is the transference of risk on a macro scale. Like, for example, let's say you say, I don't want to have a lot of on-site inventory because from a public risk standpoint, that's just more opportunities for large releases from my plant that could go into the community that I have to manage, and there's a high risk of that. So yes, I like minimizing tank inventories, et cetera, but if you take it to an extreme, then perhaps you've transferred all the risk to the transportation sector unless you've eliminated the process. You've got to bring a lot of product in and export a lot of product out because you're not storing it. So there's a balance between efficiency and economics and reliability and all the reasons why we like large tanks and things, and inherent safety. And you need to evaluate that carefully. There's even a favorite one that a lot of people brought up with ISD. ISD, of course, has been controversial for safety, security. I testified in a Senate committee on should it be regulated? And, it's people who are not in the industry look at this and say, of course you shouldn't have such a large chemical that's that hazardous anywhere near this community, and so forth and so on. And so they're very distrustful. So there was a great move to eliminate all chlorine that was used for water treatment all over the country, particularly under the EPA RMP, but also then under the Chemical Facility Anti-Terrorism Standards. And, this might be simple, that now we can use sodium hypochlorite bleach, but somewhere there's probably a bleach manufacturer that isn't necessarily manufacturing to the same level of exposure as they were before. So, it's like squeezing a balloon, right? That you get some potential to expand the hazard where you didn't intend. I'd also want to mention that the most effective ISD applications that I've seen, and there are companies that have achieved this, is where they institutionalize ISD to where it's a matter of company culture. How have they done that? Well, we gave you a preview on that one poll, but they implemented policy and procedure. They had management behind it. Everyone's accountable. It's in everyone's objectives. It's evaluated. There's policy. There's goals and incentives even. And then they've developed tools and checklists and auditing protocols and even their own indices in some cases to try to say that this is really important stuff. It's not a one-off, one-time. We play around with it a little bit. We have a checklist that we may use and ask a few questions. This is an integral part of their strategy for process safety. Now, I wanted to just close by mentioning one company that we worked with, and they were an international chemical manufacturer, and this was a recent one. They had 5 manufacturing sites around the world that were concentrated large chemical complexes. And what we did is we went to each of these, and we started at their headquarters one, and they were curious about ISD. It was almost like, we hear a lot about it. We want to see it in action. We'd like to judge for ourselves whether we should be really entertaining this in a big way. So we did 5 studies. Each one took about 4 days of session time. If that was a HAZOP, each of these studies would have been more like 20 to 30 days or more, because focusing just on the ISD as a special study was simpler. And was it productive? Well, yes. I mean, the company was pretty impressed because they had HAZOP'd all of this, but we ended up with 193 recommendations for these 5 processes. And they're at this point implementing some form or fashion of every one of them. That's about 38 recommendations per study in 4 days. So think about this. These were existing processes. A lot of people don't believe there's anything you can do about an existing process unless you want to go broke, rebuilding the thing. And I'm going to show you the kinds of smaller situations that we identified that were just almost a no-brainer in some cases. They were free in some cases. And then some more expensive ones that actually were worth it. And they liked it. And that's why they're adopting this in a bigger way. So what they got out of this is they realized that nothing wrong with the HAZOPs and LOPA studies and everything else that they're doing. They were doing them as well as anybody else. But this is a different focus, and that different focus brought a different perspective. And some of the same team members had missed some key opportunities because they were sort of shy to ask. They just expected that the focus was on identifying additional layers of protection. They actually learned a little bit about hazards more in depth than they thought because we're attacking the hazard head on. They therefore had us do some training, and the training ultimately was over 200 people. And curiously, the CEO was hearing about this, so he came and brought some of his VPs, liked it so much that he mentioned at the end of the training that we really have to do this. Competitively, we have to do this. We can't afford an accident. He said nothing will stop in our way in terms of our company's ability to succeed financially or technically, except a process safety catastrophic accident. And I want this to be done. So it was very inspiring. And all of the process safety related personnel attended one, and then we expanded that out to engineers and so forth. And we helped them develop a company policy and some guidance documents on how to do this. So then they had a standard procedure. And in the end, we took all those recommendations and we made sure that they were getting action on them by helping them to prioritize them. And priority one isn't, just the cheap things. It's the things that they felt easily implemented and could be considered as a high priority. And that they they felt very comfortable recommending, and they wanted to address right away. They were kind of excited about these possibilities. The priority two were some things that definitely needed more screening. They maybe weren't as high a priority to them. They weren't going to make as big of a safety impact, but they sounded important. And three were things that had a lot more effort, a lot more cost, no less interested in them, but they just needed further study. So recognizing that inherent safety studies on existing facilities are not necessarily easy, but what was interesting is that priority one was given the most. In other words, they were anxious to address and change the majority of these. So now what they've done is they've adopted this, and in conclusion, this slide is really the words from them. They said that they are now going to implement it in all phases of the projects that they have, from the early stage development all the way through to operating. They're not only going to do the layer protection concept. What they mean is typical PHAs and LOPAs. They're going to do the ISD concept as well. That they've seen now that they can eliminate needless equipment, basic process control systems, safety instrumented systems, pressure relieving equipment, etc., just by changing designs that they had intended, eliminating hazards and so forth. And they feel that that's going to make a huge difference in terms of the operational and maintenance, human errors, and costs of these things. We also got them to focus on some of the high hazard chemicals that they were storing in excessive quantities, and the public and community and environmental exposure we think was greatly reduced. There's lots of examples. You can see this later on, but things like, we weren't shy to say you've got excessive transportation of hazardous material and going all through the plant. And now you're talking about expanding the plant where you're going to double that. Maybe it's time to look at an on-site plant that sounds more hazardous, but actually has a direct connection, is a lot less hazardous. Eliminating storage tanks, eliminating equipment, changing technology, getting rid of toxic substances, and so forth and so on. And these were all existing plants. So I'll finish by summarizing that ISD, as it shows, can clearly be used throughout the entire process life cycle, and especially for existing processes. And I hope you all try that. And that these 4 strategies, as simple as they seem, have very wide applicability. Many, many interesting things are caught in the net of those 4 strategies. It represents a substantial opportunity for risk reduction, and the shame of it is it's not commonly used to its fullest extent. And so whatever we can do to expand the usage of it, I think you'll be happy. And be careful, though, because even what seems like an obvious and simple ISD application may cause unknown hazards. You have to not be too anxious about implementing the first thing you can think of. And lastly, the more that you can ingrain this into the safety culture and have strong commitment and not just consider it a one-time study that there's no way that it's useful anymore, we're way past that, the better off you'll be. So I hope that this has been interesting. Thank you for your time, and I'm happy to answer some questions, Sam.
All right, great. Thank you so much, Dave. It really is an interesting topic. It's just not as prevalent as it should be, but it's really very applicable to our industry, and it should be more widespread, than it is. So we have a few minutes now to answer some questions from the audience. And while you answer questions, I'd like to put up the first poll again and just allow you an option to state that if your company does not do anything in regards to ISD studies that we did not have as an option. So if you don't mind, we'll revisit this poll, and I'll ask you some questions, Dave. All right, the first one I think you addressed, but I'll just ask you to double check. Can ISD studies be applied for old plants or only for new or upcoming facilities?
Yes, I showed here an example of this company that it was all existing plant. In fact, some of them were built 20, 25 years ago.
Right.
We just weren't shy to say, well, why do you have this filter downstream of the reactor? It plugs all the time as we have this discussion. It's try to catch catalyst. Why not change out the type of catalyst? Why not have a different design? Things like this. So what we did is we weren't shy to say anything of any scale, and the company was willing to listen. And then out of that came a lot of good ideas, some of which are cheap and some are going to be investments. But yeah, useful for both.
Okay. So along those lines, can you give an example of an ISD recommendation made on an existing facility? Yes.
As for example, we identified unnecessary equipment a lot. They had 3 intermediate storage tanks. When you ask why, the answer is usually for capacity, you never can tell. Also for convenience when we have turnarounds and shutdowns and so forth. But it was, excessive. And that comes with 3 times the maintenance and inspection and 3 times the cost if you're building it, and so forth and so on. And so there's a minor example. There's plenty of examples. In fact, I was saying we had, I think it was like 190 recommendations on just these 4 studies. Every one of them was a recommendation on an existing facility.
All right. I'll ask another one here. How much does the cost component affect an ISD study? Not sure if that's about discussing the study component itself, or I am assuming more of the recommendations.
Well, the study costs whatever it costs to get people together for, sufficient time, plus writing a report, et cetera, and then all the follow-up. So there is that, but that's trivial compared to the benefits you get. The cost of implementation of a particular recommendation varies with what you're suggesting. For example, switching out a solvent, they hadn't really thought about it. There is another solvent. Really, the next time we order, let's order a different solvent. There's not much cost difference whatsoever. Whereas let's change this whole equipment around, that could be expensive. So what you can do is use any conventional cost-benefit analysis to figure that out, but then you have to evaluate the risk differential. So if in the one case you have fire and explosion risk and one you don't, that may be a very, very powerful incentive, whether it can be quantified or not.
All right, great, thanks. So I took the poll down, and I just wanted to, mention that there were quite a few votes for, my facility doesn't do anything in terms of ISD. So along those lines, the next question that we have is, we have nothing in place right now. How do we start implementing ISD from scratch?
Well, what I found really effective is to do what I call a reference pilot study. In other words, if you see it and you participate in it and it works, you're going to be pretty impressed and excited about it. And then you can train the trainer, if you will. So that's how we started with everybody we work with, is they'll say, we're curious about this. Can we try it together? And we'll lead in this and coach them on how to do it and teach their people to do it themselves, or help them with additional studies should the first one be successful. And they almost always are, because they're literally eye-openers, especially if you think that you've done a good job on your HAZOP studies, what-if studies, what have you, LOPA studies. And then you go through with an ISD viewpoint and you find additional things that you've been living with, and you feel like, well, why have we been living with that risk? So this is the incentive, is to do something powerful like that, and then have your management appreciate it and back you on doing more such studies. If they're not supportive, you're going to have a lot of bright ideas that don't go anywhere.
Right, exactly. All right, I think we have time for just one more question. What is the best in class use of institutionalized ISD that you've seen?
Well, there are some companies that have everything that I've said, including the ones we've helped that I mentioned, and others. But I know some companies have believed in this for years and years. And you see it because if you talk to their research chemists, it's part of their procedures that they must follow, that they identify hazards and they look at alternatives and they document that they actually considered things, and they rule them out only by the fact that they're not a better alternative for some reason. So, it's the best case of institutionalization would be where they have systematic management systems, controls, documented processes where they're actually doing this, rather than they're shooting from the hip, that if the team leader of a PHA happens to think of a good question and raises it one time, then maybe, yes, that's a good point. We can make an inherently safer recommendation here. So that's the two extremes, other than those that aren't doing anything.
All right, great. Well, thanks so much, David. I really appreciate it. I think that's all of our time. We hope to see you at our next webinar, which is on Tuesday, September 22nd, which will review a case study on inadvertent mixing. You may may direct any questions you may have or requests on how Accutech can further assist you to info@accutech-consulting.com. And I thank you for joining, and have a great afternoon, everyone.